I want to talk for a little bit about bond rotation in a small, simple molecule and use it to draw out a couple examples that we're going to use a lot in organic chemistry. So if we have a simple single bond, right, formed by a sigma bond, that would be, for example, like an ethane, it's going to have rotation around those bonds. So here I've drawn it out, and there's rotation around this bond. Now, I've not expanded these hydrogens yet, so it isn't really obvious what that means, but let me show you really quickly what I mean by that. If we take this, and I'm going to sort of draw these hydrogens three-dimensionally, right? So let's say that this hydrogen is coming out at us, and this one is going away from us back into the screen. And then this hydrogen would be straight up like this. So this would be tetrahedral. We would have our other carbon then coming straight out this way. And if I drew that, I could sort of draw it in two ways. I could draw that other hydrogen up like this, sort of the mirror image of that over here, right? So we have that sort of a situation. But couldn't I also take this entire molecule? Couldn't I also draw it like this? Here, let me draw it for you in another way. Could I write this bond here just straight like that? And then could I put this bond coming kind of at us? And that one away from us? Is there anything wrong with drawing it like this? Well, there isn't, right? There's two separate ways to draw it. And all that I've really done here to change these is I've rotated around this bond. So the question becomes, which one of these is correct? Well, they're both correct ways of drawing it. And actually, in solution, you'd have both of these because there'd just constantly be rotation around that bond. That's just how molecules contain energy, is there's always movement, always rotation and movement around those bonds, right? So what we're going to do here is I'm going to show you a new way of drawing these to really see that rotation and how it plays out a little better. And then I'm going to talk about the energy that starts to entail for us. So to do that, I'm going to draw an eyeball right here. I know it's a beautiful eyeball. I'm very good at drawing these things. And we're going to look down that carbon-carbon bond. So imagine instead of looking straight on at this thing that you're rotated around and you're looking down that carbon-carbon bond so that those carbons eclipse each other. That's going to allow us to get a perspective and see what's happening around this bond. So if we look at those two eclipsing each other, what we would see in this case right here that I've drawn is you'd see something kind of like this. And here, you know what, I'm going to go ahead and move everything over so we have room here, right? And in the meantime, I'm also going to draw this one where I'm looking down the bond. So, right, so we're going to do this for both of these. And I want to show you kind of what it looks like. So first of all, in the very foreground here, okay, this is the foreground where the eyeball is, you're going to have a carbon that I'm going to sort of draw as a big sphere or blob here. And then it looks like we have two hydrogens coming down like that and one hydrogen coming up. So if we rotated our view around, that's what this front carbon would look like. Now I'm going to draw the back carbon kind of in a blue, sort of a blue color so we can see it, right? And you'll notice with these Newman projections, these are called Newman projections, that I draw the line sort of so it looks like it's coming from behind there. So you notice that you don't see any of it on top of that black circle. That's how we show that this is the rear hydrogens. So if we looked at this one, oh, sorry, not exactly correct here. If we looked at this one, you notice that these two hydrogens right here are on the same plane, right? They're in line with each other. They're what we call eclipsed hydrogens. So what I'm going to do is I'm going to draw this hydrogen right here like this to show that it's eclipsed. Where would all of these other hydrogens be if we look down at that angle? Well, we notice that they're actually all going to be quite eclipsed right there. So that's what we're going to get when we look down those bonds. Well, what about the lower example here? what happens when we look down those carbons? You're going to get, in the front here, we see one coming straight up. All right, so we've got a situation like that in the front. And if you look, what's happening in the back? Well, if you look this one, these two are kind of on either side of it, right? And that one's right down the middle. So what the back is going to look like, and again, I'll switch colors for us, is directly between those is where that central hydrogen is. And then we notice, of course, we have another one right here, all equidistant apart. So right here, what we're going to call this is these two are eclipsed. Right? Eclipsed. And these right here are in a staggered. So these are in a staggered formation. Now, what does that do for our energy? Well, you guys might already guess which one of these is higher in energy. What do you think? Go ahead and pause it, decide, and then tell me what you think. All right. If you said that this one is higher in energy, you're correct. The reason is something we call steric hindrance. Steric hindrance. Now, that's the reason that probably jumped out at you, and that means that those are just literally in each other's way. The electron clouds are bumping into each other, all right? Now, that has something to do with it. I'm going to show you in a minute that there's actually even more going on here. But that is one reason why those two are eclipsed, why it matters. Now, both of these are ethanes. I'm going to add one more layer to this, and then we'll kind of talk about energy even more. I'm going to say, hey, what if we had a butane? What if we had a butane? Now, in a butane, we're going to have to choose one bond to look down for a Newman projection. So what I'm actually going to do is I'm going to choose to look down. Draw my eyelids in here, eyelashes in here so it looks like an eye. I'm going to look down this bond right here because that's going to give us the best Newman projection to understand this. So I'm looking down this central bond. So the front carbon is going to be this one right here. And the rear carbon is going to be this one right here. So let's go ahead and draw this. Newman projection. All right, so let's try this. What do I have attached to that carbon? Well, I have 3 lines, right? So what 3 lines do I have? And let's go ahead and bring it down a little bit. What 3 lines do I have here? Well, I have one bond that has our whole CH3 on it, right? I have another bond that has a hydrogen, another one that has a hydrogen. Of course, the one that attaches to that carbon, the CH2, the next carbon in the chain, is going straight backwards, right? So we actually can't see that one, that bond. It's in line kind of with our eyesight here. Now, let's draw the other one. Do you notice how I kind of drew it as a zigzag here, right? Like it kind of goes like this, right? That's the line angle formula for this. Why is it a zigzag? Well, we're about to find out. If I draw the other one, we would have our CH3 directly across from us, right? Kind of pointing up like that in the back. And we'd have hydrogen and a hydrogen in that back carbon. So this is actually the lowest possible energy conformation of this structure. Because the largest things that are attached, those methyl groups, are actually completely anti to each other. We call this anti to each other. And actually, oftentimes this can be called anti-coplanar because all of this right here is in one plane. So these are coplanar in the same plane, but anti to one another in the molecule. All right? So this would be the lowest possible energy conformer. So let me draw real quickly what this ends up giving us. If we took butane, which is right here, we could actually sort of start to spin around that bond and notice a lot of different structures that we could get. Well, what are those structures? I'm going to draw them for you. If I start to rotate this thing around, like this, what am I going to end up getting here? Well, at a certain point, I'm actually going to start eclipsing, right? As this bond rotates, I'm going to start eclipsing these. So the next possible thing that we're going to get is we're actually going to get a hydrogen, right, that moves right there. We're going to get this hydrogen to move right up against this guy. And we're going to get our CH3 here to eclipse with this one. Now understand, when I draw these eclipsed, what I actually mean is they're basically in front and in back of each other. I have to draw them off to the side so you can actually see it, but these are fully eclipsed with one another. So if you look down the bond, you would not see the front one would be blocking the rear atom. All right. Let's make this again the same size. Okay, so let's draw our couple options. Now I said that as it rotated around, this is what we'd end up with, right? As this rotates around, we're going to end up with this, okay? Well, what happens as we keep rotating it? What's the next one going to be? So I'm going to move this over. A lot of moving around here. Okay, what's the next one going to be here? Well, as we keep rotating around, we're going to now have this CH3 no longer eclipsed, right? It's going to be here. We're going to have our, because this one is now rotated all the way up here, right? It's now in between there. And we're going to have our H right here, and then we're going to have this H down here. That means that sort of in the back here, we're going to have our still CH3 here. Hydrogen here. Hydrogen here. Now, this is a staggered conformation again, right? So we're saying, hey, this is pretty low energy. This is good. But there's something going on here. These two bigger groups are, even though it's staggered, they're still pretty close to each other. So they're starting to have some steric interference. Okay, that steric hindrance we end up calling gauche. Okay? Gauche is actually a word that means, the literal translation of gauche is awkward. So what that means is, oh man, it's staggered. It seems like it should be good, but it's a little awkward because we got those big groups sort of next to each other. They're not fully interfering, but they're just kind of awkward next to each other. All right? So that's what gauche means, and that's what we get as we continue to rotate this thing around. All right? Now, let's keep going with this. So if we keep rotating this thing around, what's our next going to be? Well, you're probably already seeing it as we rotate this around. Sorry, let me get the right color here. Rotate that around. Now we're going to have eclipsed where we have two CH3s sort of in the way of each other, right? We're going to have eclipsed here where we have this hydrogen, and we're going to have eclipsed here where we have this hydrogen. Of course, let me get rid of our old stuff. So now we have an eclipsed where we have the two largest things next to each other, and that is the worst possible situation, right? So this is going to be the highest energy. Think of a spring that has been pulled and stretched as much as it can, and it really wants to snap back, right? This doesn't want to stay like this. It wants to keep rotating. This is our highest energy conformation. Now let's keep rotating that thing. Now we have our CH3 here, our H here, our H here, right? which means we have CH3 in the back here, H, and H. All right? So this is now staggered again, right? So you'd think it's good, but remember, we don't want those big groups next to each other. So again, this one is also gauche, right? Because we have those big groups next to each other kind of there. And then lastly, we keep rotating around. We're going to have another eclipsed where we have our CH3 here, hydrogen up, hydrogen over, right? So now we have another eclipsed, but in this case, again, our CH3 is further away. And if we kept rotating this around, what we'd end up with is what we see up here. Sorry, I'll make this. And this is how the energy would end up looking. So if we graphed energy on this axis right here, and each of these were points as we rotated, of course, this one where we're staggered at the very beginning, number 1 here, staggered, is going to be the absolute lowest energy possible. So let's say that's the lowest energy. And as we rotate, here we come into an eclipsed position. So let's say it's a little higher, quite a bit higher energy right here, where it's eclipsed, or number 2. Now let's say we keep rotating this. It's going to become staggered again, which is lower energy. But it's not going to be as low as it was before, because this is, remember, gauche or awkward. Those CH3s are too close to each other. So this is going to be gauche or awkward, this big groups next to each other. And then we continue to rotate, and we have position 4, where we have these fully eclipsed largest possible groups. So that's going to be our higher energy. Sorry, this should be a lot smoother line. Right, so there's going to be 4 up here where we eclipse the largest ones. And then as we go gauche again on 5, it's going to be, of course, this same energy level. Really should be the same energy level. And then we're going to go to 6, where we are yet again eclipsed. But that should be this same height, right? We're now eclipsed, but with not the largest groups eclipsing each other. So that's why we're a little lower in energy. And then finally, we're going to return to position 1 over here, where we are the lowest in energy. So that's kind of how energy relates to these as they rotate around.